Okay, number 2, we're given an initial value problem. So an initial value problem, remember, has two parts to it. It's got the differential equation, and then it has this initial condition. This initial condition is kind of vague. It corresponds to some point x naught, y naught in the plane. So you can think of this geometrically as we're trying to find a curve satisfies this equation that goes through this point. We're asked to sketch a region in the plane in which we're guaranteed a unique solution. Alright, so we're going to have to go back and use that existence and uniqueness theorem that we had in section 2.1. And so to apply that, you need to get the differential equation in this normal form, y prime equals f of xy, and if f and its partial derivative with respect to y are continuous in an open rectangle containing the point x naught, y naught, then we are guaranteed a unique solution to the initial value problem. So not only do we get a solution, we get one and only one solution. And as we mentioned in class, this theorem isn't as sharp as it could be, meaning that there are conditions that are weaker that would give us the same result. But this is the theorem that we're going to apply in this course. Okay, so to apply this theorem, y prime equals f of xy, I already have it in that form. The f of xy is the square root of x squared plus y squared minus 4. So I need to figure out when it's happy and when its derivative with respect to y is happy. So we'll go ahead and take its derivative with respect to y. We can rewrite this as x squared plus y squared minus 4 to the 1/2 power. And I'm taking the derivative with respect to y, so I treat the x as a constant. So I go through the usual machinations, and I'm going to get this. And so the question is, where are both of these functions continuous? Where are both of them happy? So let's go over to the plane. In order to keep the function f happy, I need to make sure what's underneath the radical here is bigger than or equal to 0. So I need x squared plus y squared minus 4 is bigger than or equal to 0. In other words, I need x squared plus y squared is greater than 0. Excuse me, greater than or equal to 4. Greater than or equal to 4. So if I look at x squared plus y squared equals 4, that's a circle of radius 2 centered at the origin. So that's where it's equal to 4. Where is it greater than 4? Well, that's going to be outside the circle. Remember, you can always check. If you have a closed curve, you check a point inside, check a point outside, see which region satisfies the inequality. So this is where f is happy. What about its derivative with respect to y? Well, now this square root is in the denominator. Okay, so to make the denominator happy, not only does what's inside here have to be bigger than or equal to 0, it can't be 0 either. So to make the derivative happy, I need to get these things strictly bigger than 0, which means I'm not going to include the circle itself, because that's when the derivative is going to be undefined. Alright, so this is my region then. This is my final answer. It's everything outside the circle x squared plus y squared equals 4. If I pick any point x naught, y naught in that region as my initial condition, then I'm guaranteed a one and only one solution to the initial value problem. So that'll do it for number 2, and that'll do it for quiz 1.